So the speaker today is Professor Dustin Mixon from the Ohio State University. And today he's going to talk about optimal arrangements of 2D lines in C to the D. Okay.
All right, thanks for having me. This is some work that I did with Joey Iverson and John Jasper, friends of the seminar here, I think. So, and this was supported by the NSF and the Science Foundation. The problem that we're going to be looking at, it's really a conjecture. It's still a problem. I haven't solved it. Joey, John haven't solved it. It's the D by 2D conjecture. And in this form here, this is the weak form. This is just saying that for every D, there exists a D by 2D matrix called an equiangular tight frame. And we'll tell you what that means here in a bit. Bottom line, we're going to be talking about this conjecture. We're going to show you a couple of infinite families of these equiangular tight frames. This is partial progress towards the D by 2D conjecture. And we're going to show you a conjectural construction for all dimensions, and we'll actually prove that these constructions work for the first 162 dimensions. So here we go. Before we started working on this problem, there were a bunch of examples of D by 2D ETFs. These are all the values of D for which things were known, and we'll cover that background before I show you a trick that was used to fill a bunch of these gaps. These are the gaps that we need to fill in order for things to work for all dimensions. The first move was made by Joey Iverson and his student Kian. They came up with this concept of doubling that filled in these columns that you see in blue. And then later, he enlisted myself and John Jasper to generalize this technique. We ended up coming up with a way to double these things called conference graphs. I'll tell you about that later. And then when we looked at the structure of these objects, we noticed that a lot of them were something we're calling two circulant. And when we try to hunt for ETFs with that structure, we end up getting all of these things. So that's the vibe of the talk. And we're going to start with some background. Okay, so we are interested in arranging lines in either RD or CD with the property that the minimum interior angle is as large as possible. The smallest interior angle, like this one right here, that is the smallest interior angle for these three lines. That's too small. I can make it bigger. Here in this case, the smallest interior angle amongst all pairs is 60 degrees, and that looks pretty good. You can talk about this in terms of unit norm representatives for each line. So you take a unit vector that spans each line, you shove them into a matrix. Let's say it's D by n because there's n lines in D dimensions. And then if we're interested in the smallest interior angle, making it as big as possible, we're interested in the largest absolute inner product, right? That cosine of that interior angle. And we want to minimize the largest absolute cosine. Okay. So we have this problem set up. How do we know that we have something optimal? Well, here's some examples. We have, turns out when you take antipodal vertices of a hexagon and you draw a line through them, they all collide at the center, call that the origin. And this is an optimal arrangement of three lines in R2. We saw that on the previous slide. You do the same move with vertices of icosahedron, you'll get 6 lines in R3. That happens to be optimal. There's a story in the complex case where it turns out this 3 by 9 matrix, the columns span complex lines that minimize coherence. How do we know that? Well, there's this thing called the Welch bound. This says if you have n vectors in RD or CD, then there's a lower bound on the coherence. It's at least this nasty square root. And furthermore, you can achieve equality in this lower bound precisely when your collection of vectors satisfies two properties at the same time. First, you want equiangular, so the absolute value of the inner product between any two equals the same number, this mu thing. They're all equal to mu. And then furthermore, if you were to take this short fat matrix, phi, and multiply by its conjugate transpose, the result is a constant multiple of the identity matrix. This is called a tight frame. So if you're both equiangular and a tight frame, then you're called an equiangular tight frame. And this characterizes equality in this lower bound. Since you achieve equality in that lower bound, it means everything else has equal or worse coherence to you. So you have minimum coherence. So you're in optimal line packing. So if you're equiangular, then equiangular and tight, then you're in optimal line packing. There are other cases where ETFs, equiangular tight frames, don't exist. It's sometimes not possible to achieve equality in this lower bound. But when you can, you're definitely in optimal line packing by virtue of the Welch bound. So, for example, that 3x9 matrix, this complex matrix, the columns form an equiangular tight frame. Why is that? Well, you take the Graham matrix, right? Phi star phi, this is the table of all inner products between columns, and you observe that every off-diagonal entry has the same modulus. That's what it means to be equiangular. And then it's tight because you multiply by its adjoint. You get this multiple of the identity. So it's both equiangular and tight, therefore it's an equiangular tight frame, therefore achieves equality in the Welch bound, this lower bound for coherence. So it's optimal, minimum coherence possible. How are we doing so far? Any questions? Cool, cool. So let's think more about how to tell whether something's an ETF. So I just told you you want to be tight so that phi star is a multiple of the identity, and you want this, you want to be equiangular, so absolute value of inner products between different guys all equal to the same thing. So obviously, the way to look at these inner products is to inspect the Graham matrix, and we can see that, yeah, all the off-diagonal entries are equal. What we also want is for our matrix to be tight, and you can see that by inspecting the spectrum, okay? So being tight is equivalent to phi star having a single eigenvalue. That's what it means to be a multiple of the identity. It's self-adjoint, so that's equivalent. And then the spectrum of phi star is the same as the spectrum of phi star phi, except for some zero padding on the spectrum. So that's what we're saying here. Cool, cool. And then, yeah, the off-diagonal needs to be constant. Great. There's an even prettier matrix to look at. It's called the signature matrix. What you do is you throw out all these square root 5s, you zero them out, and then you throw that 1/√5 away. So it's just zeros on the diagonal and modulus 1 on the off-diagonal. So these are the algebraic gymnastics that I did to accomplish that. Accordingly, it's still self-adjoint. And the spectral condition, let's go back to the Graham matrix for a beat. So having all the eigenvalues be either n/d or 0, that's the same thing, it turns out, as g squared being a multiple of g, namely n/d times g. And when I do these algebraic gymnastics to g, I ask what's the resulting quadratic on S, I end up with this quadratic. Okay, and then the equiangular condition is just saying that the off-diagonal entries have modulus 1, diagonal entries have modulus 0. But if you were to define a signature matrix, you would just say, yeah, zeros on the diagonal, off-diagonal modulus 1, okay, it needs to be self-adjoint. But then the real interesting bit is it needs to satisfy this quadratic. So how do I satisfy this nasty-looking quadratic? That's the algebraic combinatorics sitting on the slide here. So one way to do it is using an object from combinatorial design theory called a conference matrix. So this is kind of looks like a signature matrix. It's got zeros on the diagonal, plus minus ones on the off diagonal. This is kind of weird. It's not self-adjoint. In this case, it's skew symmetric. Okay. Yeah, all the off-diagonal entries are plus minus 1. The algebraic condition that a conference matrix needs to satisfy is that C times this transpose is this multiple of the identity. Okay. Okay. Turns out there are two different flavors of conference matrix depending on the parity of n modulo 4. Okay, so if n is a multiple of 4, then up to conjugation by diagonal matrices, you're getting C transpose equals negative C. It's skew symmetric. If n is 2 mod 4, then C is a symmetric matrix. It turns out, let me shrink this. There we go. It turns out that if you have a conference matrix of order 2D, then you can play reindeer games with that conference matrix to make a signature matrix of a D by 2D ETF. For example, if C is skew symmetric, then you multiply by the imaginary unit to force it to be self-adjoint. And then the algebra works out. If it's symmetric, you just leave it alone. It's a signature matrix all by its lonesome. So this is how you get an ETF from a conference matrix. If you were to take the signature matrix and then pump up the diagonal to make a gram matrix and then factor that to get a short fat matrix, where the columns here will span lines in C2 that form an equiangular type frame. The most popular example of a conference matrix is the Paley construction. You can do this whenever Q is an odd prime power, and what you're using is the Legendre symbol. So this is a function that receives a member of FQ and asks, hey, are you 0? If so, it outputs the number 0. If not, it's sitting inside of the multiplicative subgroup of FQ. So then it asks, hey, are you a perfect square? Are you a member of this multiplicative subgroup of index 2? If so, it kicks out a 1. Otherwise, it kicks out a -1. So this is a multiplicative character that's going to be available to us. When Q equals 3, it looks like this because 0 maps to 0. 1's its own square, and 2 is not a square. You can make the circulant matrix from that function. Okay, and you'll get this 3 by 3 matrix of 0s on the diagonal, plus minus 1s on the off diagonal. Kind of smells like a conference matrix, and it almost is. You just need to pad with more numbers. You pad with 1s on the row and minus 1s on the first column. If this looks skew symmetric, you want to keep it skew symmetric. Otherwise, you would keep it symmetric by padding with 1s. Okay, and this gives you a conference matrix from the Legendre symbol. Okay, it works whenever Q is an odd prime power. And that explains everything that was known before the work from today's talk was commenced just a year or two ago. Next, we're going to talk about doubling ETFs. This was technology built by Joey Iverson and his student Kian Fallon. And that's going to allow us to populate all of these blue columns, including these open boxes. So previously unknown ETFs. All right, so in this part of the talk, we're going to be doubling one type of conference matrix. And in a future part of the talk, we'll be doubling the other type of conference matrix. We're going to start with the skew symmetric. Okay, that's the part that Joey and Kian sussed out first. So we'll do that. So the inspiration for doubling comes from a move that's been known for a little bit in the conference matrix world. If you have a skew symmetric conference matrix, then you can double it. You can make it have twice the size, twice the number of rows and columns by dumping C in certain places and adding or subtracting I as appropriate. Kind of makes sense that you need to do some sort of modification to the diagonal because you need all plus minus 1s on the off diagonal, and C has 0s on the diagonal. So it turns out that adding I up here and subtracting I down there does the trick. So you can just verify the relations that things work. You take the transpose, it equals negative the original, so it's skew symmetric. And then you multiply by its transpose, and you do some algebra that's annoying to look at, and you end up verifying that it is, in fact, a conference matrix. So it's both skew symmetric and conference. It does the job. Now, we're not terribly interested in skew symmetric conference matrices. We're actually interested in equiangular tight frames. And we can construct equiangular type frames from skew symmetric conference matrices. So it makes sense to consider what is this doubling move, what does that do in the ETF land? So for the signature matrix, what you're doing is you're doing a similar doubling move. Remember, when you take a skew symmetric conference matrix to turn into a signature matrix, you multiply by square root of -1, and that multiplication appears, so S already has I multiplied by it, but then when I do this plus I and minus I need to multiply by that square root of -1. So this is doubling in ETF land. And you might wonder, hey, can I do this to other signature matrices of ETFs? And it turns out the answer is yes. So not just for ETFs for which n equals 2D, if it's 2D plus or minus 1, it turns out you can still do this move. And you started with a D by N ETF, you'll end up with an N by 2N ETF. Okay, you're doing this modification to the signature matrix to make it go. And instead of multiplying by I, you're multiplying by some other complex number of unit modulus that's determined by D and N, the parameters here. Okay. So you can verify that it satisfies the conditions for a signature matrix, and the algebra is annoying, but it goes through and everything's great. Okay. So if you do this for the smallest non-trivial ETF, the 2 by 3 ETF, that has the property, sure enough, 3 is twice 1 plus or minus 1. So it satisfies this hypothesis. And so you turn the crank, and this produces a 3 by 6 ETF. So I take this hexagon looking thing, and it is converted by doubling into this icosahedron looking thing. Now a 3 by 6 matrix, N does equal 2D in that case. So I can run the machine again and get an even bigger ETF. I end up with another guy of the form D by 2D. I can keep running this machine over and over again, collecting power of 2 on my dimension. What this is saying is, if you want to show that D by 2D ETFs exist for every D, once you know it's true for all the odd dimensions, you're going to get it for the other dimensions for free, just by this doubling theorem. There's a particularly nice example of a ETF that's not quite redundancy 2. In this case, N minus 1 is twice D plus 1. Okay, so it's just 1 shy, or 1 in addition to 2D. So we can run this doubling thing to that construction. The way they do it is they take their conference matrix, their skew symmetric conference matrix, and they rip out the core. Okay, this is where the off by 1 is coming from. And that core, you can force to be the signature matrix of an ETF. There exists a phase that you can throw in here that makes it satisfy the conditions. And if you were to run doubling on that skew conference matrix, you'll end up with a N minus 1 by 2 N minus 1 ETF. There's a particularly popular skew symmetric conference matrix that comes from a Paley construction. Whenever Q is 3 mod 4, you'll get a skew symmetric conference matrix, and that in turn will give you an ETF that's Q by 2Q. And that is what fills in all of this part of the table. So these are new ETFs as of like a year or two ago. Okay, so the skew symmetric conference matrices that seem to be playing a role here, if you use epsilon imagination, you might think that they're related to Hadamard matrices. Like if I were to just dump a 1 into each of these diagonal entries, it would kind of look like a Hadamard matrix. Is it? And yeah, it is. In fact, you look at the inner products between any two columns, it'll be orthogonal. In fact, these are called skew Hadamard matrices because Except for the diagonal, they are skew symmetric. And skew Hadamard matrices are in one-to-one correspondence with skew conference matrices. And if you've heard of the Hadamard conjecture, there's something called the skew Hadamard conjecture that says, yeah, these things always exist. So in particular, if you believe the skew Hadamard conjecture, then you believe in the existence of all these skew conference matrices, and therefore you can run doubling on those things. And all told, if the skew Hadamard conjecture is true, then you'll have the d by 2d conjecture holding for every even dimension, and even every dimension that's 3 mod 4. So 3 out of the 4 cases are covered by the skew Hadamard conjecture. It does not, at least not naively, we don't know how to get this to fill in the final gap, which is 1 mod 4. So we actually came up with other technology to treat 1 mod 4, and that's what this next part of our talk will be covering. We're going to be doubling things called conference graphs, and that's going to fill in some more holes. It's not going to fill in all of the holes in these columns that we know of anyways, but it'll get us closer. So let's get into it. So this is going to be a doubling theory for the other type of conference matrix, namely the symmetric conference matrices. So if you have a symmetric conference matrix of order n, this is corresponding to a conference graph of order n minus 1. And what you're doing is you're just ripping out the core of that matrix. If you take the sign pattern of the core, that determines the adjacency matrix for a graph and its complement. And if you inspect the properties of those graphs, they will be, it'll have strongly regular properties. So it'll be a regular graph in that every vertex will have the same degree. And even more so, 2 vertices will have the same number of common neighbors depending on whether they're adjacent or not. So in this case, 2 adjacent vertices have no neighbors in common, whereas 2 non-adjacent vertices have a single neighbor in common. So these parameters are collected in here, and accordingly, A and B have really nice multiplication properties, it turns out. So if you were to square A, it'll land back into the span of A, B in the identity matrix. Same if you square B or if you multiply A and B. So A, B in the identity, they span what's called an adjacency algebra. It's a commutative star algebra. And it's super useful for various combinatorial properties like what we're discussing here. Turns out if you have a symmetric conference matrix of order n, you can use that to create an ETF of size n minus 1 by 2 n minus 1. So you're doubling the core, the conference graph. The way it goes is you take the core, you rip it out, and you double it. So the signature matrix you end up with looks just like the core you had before, and then you wherever you had pluses and minuses, you now put alphas and betas, which are appropriate to the dimension. There exists a correct choice of alphas and betas that make S a signature matrix. And it's just a matter of verifying the polynomial relations. Okay. So in particular, if Q is 1 mod 4, then you're dealing with the Paley graph that gives you the symmetric conference matrix, and it ends up giving you an ETF of size Q by 2Q. And this produces already everything you see in green here. We're filling boxes that were previously unknown. Okay. The last part of the talk is going to be about 2 circulant ETFs. So for this part of the talk, well, maybe I should tell you where these ideas came from. So if you do the doubling moves that I've been sharing with you, and you look at the short fat matrix that comes out of it. I've been telling you things in terms of the signature matrix, but you'll recall that there's a short fat matrix under the hood. If you inspect the short fat matrix, you'll notice that it has this emergent structure. it looks like a couple of circulant matrices sitting next to each other. Okay, so 11 by 22, this was the first example of a new ETF of this size that came from doubling, and it has this emergent structure. And then 17 by 34 was the first new example that came from doubling a conference graph. That's kind of curious that these circulant matrices are popping up. If you're unaware, a circulant matrix is a matrix that looks like this. So it's completely determined by the first row, or equivalently the first column. All of the other rows are just circular translates of the previous one. If you were to stack a bunch of circulant matrices against each other, we would just call it a T-circulant matrix. So this is a 3-circulant matrix. We're interested in D by 2D, so we're going to mostly be thinking about 2-circulant matrices. Okay. When we observed this 2-circulant structure popping out of our constructions, we started looking around and noticing that this T-circulant structure seems to be all over this equiangular tight frame problem. So people are particularly interested in extreme, where you have the most lines possible. This is the subject of Gerson's bound. So this says that if you have n vectors in d dimensions that form an equiangular tight frame, then n can't be too big. In the real case, it's at most d plus 1 choose 2. And in the complex case, it's at most d squared. There's only 4 known examples of ETFs that achieve Gerson's bound in the real case. The first example you've already seen, it's the 2 by 3, the vertices of a hexagon. That's not T-circulant because it 2 and 3 are relatively prime, so that doesn't work. But another example that you've seen, the 3 by 6 coming from the icosahedron, that ends up being T-circulant. And there are 2 other cases, the 7 by 28 and the 23 by 276. These happen to be T-circulant as well. So that's kind of curious. In the complex case, it's conjectured that in every dimension, there's going to be an ETF with d squared vectors in d dimensions. And furthermore, it's conjectured that they have additional structure. Like it's conjectured that they exhibit a lot of structure, and as a consequence of that structure, they end up being T-circulant, it turns out. So there's like maybe T-circulant is interesting beyond the story that I'm telling in this talk, but let's focus on D by 2D. So I told you when we double an equiangular tight frame or a conference graph, we end up with what we observe to be T-circulant. And so we see that emergent behavior highlighted in red here. We think that there's always going to be a D by 2D conjecture, a D by 2D ETF that happens to be T-circulant. So it's not just restricted to the red dimensions you see here. So as a feather in this cap, as evidence in favor of this conjecture, we can already prove that whenever Q is an odd prime power, there's going to be a 2-circulant D by 2D ETF, where D is either Q plus 1 or half of Q plus 1. And this is coming from Paley construction. What we do is we can look at a signature matrix and suss out what the automorphism group is. So the symmetries of the lines is given to us from the signature matrix. And then we can suss out from the automorphism group whether it's T-circulant. We hunt for permutation of the appropriate cycle type, and then we extract the T-circulant structure from that. So we run that machine on the Paley conference graph, and it's double, and we're able to show that these things are in fact T-circulant. So not just the doubled ETFs that we observe empirically are two circulant. It's like infinite families of two circulant ETFs. And that fills out this part of the table. So there are still some dimensions in black, and there are still some open boxes here. But we're not done with the talk. I'm also noticing that I'm running through this talk at lightning speed. So if there are any questions, feel free to pop in. Otherwise, I'll keep going at lightning speed. Cool. So you want a two circulant ETF, huh? So it's going to be a D by 2D ETF. It consists of a couple of circulant matrices. Let's call them C and D. Okay. I want this to be two circulant. I want this to be an ETF. So if it's two circulant, and I want to check the angles, I want it to be equiangular, there's actually a lot less things to look for. So C star C is also going to be circulant, as is C star D. Like all of these blocks are going to be circulant matrices. And so the first row of this circulant matrix is going to determine the rest of this circulant matrix. Similarly, the first row of that guy and the first row of that guy. The first row of D star C is determined by the first row of C star D because these are self-adjoint. So there's a lot less numbers to check. So that's interesting. But there's even more structure that emerges from this two circulant structure. And that is circulant matrices commute. So if I want phi to be a tight frame, that means I want CC star plus DD star to be a multiple of the identity. That's what this says in blue. But since these matrices commute, that's giving me a relation between C star C and D star D. That's this thing. So D star D, this block in this gray matrix right here, is determined completely by C star C. Okay, so I told you we had only a few things to check. We actually have even fewer things to check on account of this additional structure. All told, if you were to take the number of real variables that determine a two circulant ETF, and you subtract the number of ETF constraints, you'll end up with a positive number, this particular number right here. So there are more variables than constraints. That's telling us that these things want to exist, okay? And this is the subject of the strong D by 2D conjecture. This is saying that not only do these things exist, these two circulant ETFs, there's going to be a real manifold of a very particular dimension of these guys. And we're stating that this conjecture holds whenever D is not 4. I'll give some comments later as to why 4 might be special. Okay, so it turns out you can check whether the strong D by 2D conjecture holds for any given dimension. There's a routine that I'm going to show you. So this is one dimension at a time. The machine is, you get an approximate solution that you construct by gradient descent or something. You do some sort of local method to find something in MATLAB that doesn't exactly satisfy the constraints, but within numerical precision satisfies them. And then you conclude by some technology I'm about to describe, you conclude that there actually is an exact solution nearby. Okay, this is kind of the neat trick. It's called Newton-Kantorovich. And the way one could think about it is you imagine running Newton's method. Okay, so I'm talking about Newton's root finding method. So you have a point and you ask, is this a root? And you look at the function value and say, no, that's not 0. But you can use the derivative of the function to inform a better choice, something that's closer to being a root. Okay, you linearly approximate your function, and that sends you to a better approximation of a root. So that gives you something even closer. You do it again, you get even closer. And you could ask yourself, is this going to converge to a root? And at least in this two-dimensional picture, you can say, well, yeah, it should, unless F makes a left turn and manages to avoid reaching that x-axis. But I know that it won't make such a sharp left turn if I can control the second derivative. Okay, so if I have some sort of control over the second derivative of this function, I know it can't turn away, so it's forced to cross the x-axis. So there has to be a root nearby. And Newton-Kantorovich is a technique that allows you to use this this intuition that's specifically to one or two dimensions and transfers it over to the multidimensional setting we have with multiple variables and multiple constraints. In addition, Newton-Kantorovich tells you that not only is there going to be a solution nearby, but the dimension of solutions, there's going to be a manifold of dimension equal to the number of variables minus the number of constraints. So that's the story there. So that tells us that not only do we have d by 2d ETFs up to dimension 160, 162, there's actually an entire manifold of these guys of the appropriate dimension. We don't know everything there is to know about the d by 2d conjecture. It would be nice to have an explicit solution for all dimensions. We have infinite families, but we haven't been able to tackle all dimensions just yet. For the number of variables versus number of constraints, we're able to do a one at a time type analysis that factors through Newton-Kantorovich. It would be nice to have theoretical tools that could treat multiple dimensions simultaneously somehow, maybe an infinite family. The strong d by 2d conjecture cases on whether d equals 4. We believe that there is a unique 4 by 8 ETF up to isometries, or just up to obvious equivalences. We tried to prove this using Grosvenor basis calculation, and the computer gave us the middle finger. Like there's too many equations kicking around, but we suspect that someone could be more clever than we were to make that go. I told you the skew-Hadamard conjecture gives you 3 out of 4 of the dimensions for the weak d by 2d conjecture. It would be nice to close that out somehow. Like, is there a way to suss out dimension 1 mod 4 from skew-Hadamard? That would be nice, or just some other version of Hadamard. Like, does there exist a Hadamard conjecture that implies weak d by 2d? That would be great. And then one more thing that's kind of puzzling. I told you that there's some local method that we do to find a numerical two-circulant ETF, and that's the input to Newton-Kantorovich. In practice, when we run a local method, we do not get stuck in a local minimum. We go to the global minimum. And this is not characteristic of the usual energy minimization problems on the sphere. You normally are wrought with local mins that give you a bad time. And the fact that empirically there are no spurious local minimizers, that might open up the door to tools from, say, geometric invariant theory or symplectic geometry to provide at least an implicit proof of existence of these things. And that would be interesting. This was my talk. It was based on a couple of papers, one of which exists, and the other one will exist soon. That's my talk, and I'll entertain your questions.
Okay, thank you, Dustin, for the talk. So are there any questions?
I have questions.
Mm-hmm.
Thanks for the talk, Dustin. It's very nice.
Nice to see you.
First, I can see the icosahedron. I can see what happens in dimension 3, but I can't figure out what happens in dimension 2. So in dimension 1, I guess you're just taking the same line twice. What happens in dimension 2?
So in dimension 2,
Like
you
4
could
lines?
take, yeah, you get 3 lines in dimension 2 that
I thought
like,
D by 2D.
oh, for D by 2D, this is a complex phenomenon. So you
Oh,
can, so you
oh,
could view in the complex case. So
it's a POVM.
think of the projective uh, projective space. So lines in C2 form a sphere. They form S2. So if you were to take the vertices of a tetrahedron in S2, then those would correspond to an ETF of 4 lines in C2.
Okay, yeah, now I see it. I forgot that you're over the complex. So my question is about the cyclic group action. Suppose you had 2D D by 2D matrix, and you had the cyclic group acting on the coordinates as you do. Do you have other examples where there's more than 2 orbits, where there are could any vectors be stabilized by an element of the cyclic group? So here you've got everything breaks up into 2 orbits under this nice cyclic action. Are there other things that can happen with the cyclic group?
So let me. So for example, so this isn't D by 2D, this is D by D squared. For the D by D squared ETFs, not only do you get D separate orbits under the action of the cyclic group, you can also have the cyclic group act by modulation on the same collection of vectors, and that'll break it up into D orbits that like are transversals of the original orbits. So in particular, the Heisenberg-Weyl group is acting on these guys, all translations and modulations. So there's a lot more symmetry that's popping out. There is more symmetry also in these maximal examples. I don't think, oh, I would bet that there's more symmetry in the icosahedron as well. I mean, just look at it, right? It's more than just rotating. So, yeah. So,
yeah, I'm just asking about the cyclic permutation of coordinates. If I had D by 2D, is there anything else that a cyclic permutation of coordinates could do with an ETF? Could it have more than 2 orbits on D by 2D?
So for the Cayley construction, I think there's a lot more symmetries kicking around. Yeah, not unlike how there's additional symmetries in the icosahedron. But like for the strong conjecture, I think a generic point in this real manifold is not going to have additional structure. It's just going to be the 2 orbits of symmetries. Yeah.
Thank you.